I will continue by one examples. First, let me share my file. Okay, can you see my screen now? We want to derive the thank you, the equations of motion for the system shown below using the x1, x2, and x3 as the generalized coordinate system for this system, this vibrating system. We want to use the uh, Lagrange equation to extract the equation of motion. For this purpose, we need to write the kinetic energy and potential energy. We have a system with three masses, mass M, 2m, and again another mass M. We have four springs with stiffness K, 2K, K, and 3K, which connected the masses to each other. And we have 3 degrees of freedoms. x1, x2, and x3 are considered as the generalized coordinates to extract the equation of motion. So we need to write the kinetic energy for this system. As you know, because we have three masses, we will have the kinetic energy will include three terms. The first term is due to the mass m, which is equal to half times by the mass times by its velocity squared. The velocity of mass m is x1 dot squared. Yeah, this term is for mass m. We have another mass 2m with velocity x2 dot. So the kinetic energy for this term is half times by 2m times by x2 dot, this term. And finally, we have another mass m with the velocity x3 dot. And the kinetic energy for this term is half mx3 dot squared. The potential energy in this system, we only have the potential energy due to the springs. The first spring, the potential energy for this spring is equal to half times by K times by elongation of this spring, which is x1 squared. The other edge of this spring is fixed. This one, the spring with the stiffness 2K, has two movable edges. So the displacement in this spring is equal to the difference between x1 and x2. So the potential energy is equal to half times by 2k times by x1 minus x2 squared, or x2 minus x1 squared. No different, both of them will be the same. And this is the potential energy for this spring. For this one, again, we have two movable edges, and the potential energy is equal to half times by K, which is the stiffness of the spring, multiplied by x2 minus x3 squared, or x3 minus x2 squared. No different. Again, both of them will give you the same response. And finally, we have one spring with stiffness 3K. One edge in this spring is fixed and the other edge is moving moving with x3. So the potential energy in this spring is equal to half times by 3k times by x3 squared. So we can now extract the equation of motion, but before that I should again mention that in the energy method, when you want to calculate the potential energy, the direction of the force, or here you can see x2 minus x1 or x3 minus x2, the direction and the sign of these displacements are not important, and they will not affect on your result, on your equation of motion. But if you remember, while in the Newton's second law, when you wanted to extract the equation of motion, these signs were very important, and you must consider the correct direction for the force and correct sign for your displacement. But here, these signs will not affect on your results because you want to calculate the derivative, and you will see that if you consider x2 minus x1 or x1 minus x2, the response and the equation of motion will be the same, and the results will not change. So the next step, we need to calculate um, the Lagrange equations. For this purpose, we should consider the generalized coordinates. We assume that x1, x2, and x3, according to the problem description, they are the generalized coordinates. So q1 is x1, q2 is x2, and q3 is x3. So you need to substitute for q in the Lagrange equation, and we will have, for the first equation, by substituting q1 is equal to x1, we will have the derivative of the partial of t with respect to x1 dot. This is the partial derivative of t, or kinetic energy, with respect to x1 dot. The derivative of this term with respect to time minus the partial derivative of t with respect to x1 plus the partial of potential energy with respect to x1, it must be equal to q1m. So the partial derivative of t with respect to x1 dot and x1 must be calculated, as well as the partial derivative of v, or potential energy, with respect to x1. So the first step, we calculate the partial of t with respect to x1 dot. Here, this is the t. When you want to calculate the partial derivative of t with respect to x1 dot, it means that other parameters are considered as a constant value. For example, here we have half times by 2m times by x2 dot squared, because we are calculating the partial with respect to x1 dot, so we can assume that x2 dot is a constant term. So the partial derivative with respect to x1 dot for this term is 0. For this term is, again, we have half mx3 dot squared, and the partial derivative with respect to x1 dot for this term is again 0. And only the first term, which include x1 dot, will appear in the partial derivative with respect to x1 dot. So the partial derivative of t with respect to x1 dot is equal to 2 times by half m times by x1 dot, and 2 will be cancelled out with half, so it will be equal to m times by x1 dot. This is the partial derivative with respect to x1 dot. And now we need to calculate the derivative of this term with respect to time. Okay, so d to dt of the partial t with respect to x1 dot is equal to mx1 double dot, because m is a constant value. This is the mass of the system, and x1 dot derivative with respect to time is equal to x1 double dot, which is the acceleration. The second term in the Lagrange equation is the partial with respect to x1. The partial of t with respect to x1 is 0, because there is no x1 in the kinetic energy, so this term is 0. And the third one is the partial of potential energy with respect to x1. Here, this is the potential energy. When you want to calculate the partial with respect to x1, the other terms will be considered constant. For example, this term, which includes x3 and x2, will be considered as a constant value. So the derivative of this term with respect to x1 is 0. And again, this term, which is a function of x3, again will be 0 because we are calculating the partial with respect to x1. Only the first and second term will appear here. The partial of the first term with respect to x1 is equal to k times by x1, this term, and the partial of the second term with respect to x1 is equal to 2 times by half times by 2k times by x2 minus x1 times by minus 1. And you know, when you want to calculate the partial, here this term is a function of x1. So when you are calculating the partial, it's equal to, for example, if we have a very famous formula, f to the power of n, when you want to calculate the derivative of this function f, it's equal to n times by f prime times by f to the power of n minus 1. So here we are using the same formula. In this formula, n is equal to 2, f is x2 minus x1, and f prime, which is the partial derivative of this term with respect to is x1, which is minus 1 or a negative sign. So if you simplify this, you can extract the partial of v with respect to x1, and q1 is 0 because there is no external force, there is no damper. So this is a conservative system, and the q1, q2, and q3 will be, all of them will be 0. Then we can substitute into the Lagrange equation the derivative of, instead of this term, we have mx1 double dot. The partial derivative of t respect x1 is 0, and the partial of v with respect to x1 is this term, and we can substitute and extract the first equation. So this is the first equation, and now we need to calculate the second and third equation by using the Lagrange equation. Any questions so far? Is it clear? No questions? Okay. Okay, the next one we want to substitute for x2. This time in the Lagrange equation, and instead of x1, we need to substitute x2. So instead of the calculation for the derivatives with respect to x1 and x1 dot, we need to calculate the derivatives with respect to x2 and x2 dot. So here the partial of t with respect to x2 dot, in the first term we don't have x2 dot, so this term is 0. In the second one we don't have x2 dot, so this is again 0, and only for the first one, which is equal to 2 times by half times by 2 times by m times by x2 dot, or it will be equal to 2m x2 dot. This is the partial with respect to x2 dot. And now the derivative of this term with respect to time, because 2 and m are constant values, so the derivative with respect to time is equal to 2m times by x2 double dot. The partial of t with respect to x2, of course, it must be x2. Here I made a mistake. The partial of t with respect to x2 is equal to 0 because, again, there is no x2 into the kinetic energy. So this term is 0. And finally, the partial of v with respect to x2, the first term is 0 because there is no x2 in this term. And only we will have the second and third terms, which they have the x2, and the last one, which is a function of x3, again the partial of this term with respect to x2 is 0. To calculate the derivative with respect to x2, we will have half times by 2k times by x2 minus x1. Half times by 2k is a constant value, and it will appear in the derivative, so we substitute k because this half will be cancelled out with this 2. But the derivative of x2 minus x1 squared with respect to x2, it's equal to n, which n in this case is 2, so it will be 2 times by f prime, which f prime here x2 minus x1, so the derivative of this term with respect to x2 is equal to 1, so f prime is 1, multiplied by f to the power of n minus 1, which here it will be x2 minus x1 to the power of 2 minus 1, which is 1. So we will have 2k times by x2 minus x1. And for the second, for the third terms here, again, you can do the same procedure and you can calculate the derivative with respect to x2, which is minus k times by x3 minus x2. And again, q2, which is equal to 0 because we have a conservative system. And now if you substitute into the Lagrange equation in this equation and simplify this, you can extract the second equation for your system. Okay, so this is the second equation. And now we can substitute, instead of x2, we should substitute x3 to calculate the third equation. For the third equation, we will have the derivative of partial t with respect to x3 dot and minus the partial of t with respect to x3 and the partial of v with respect to x3. And here, of course, this is q3 and this q3 is again 0. The partial of t with respect to x3 dot, this term is 0, this term is 0, and only the last one, which has x3 dot, will be appear in this derivative. So it's equal to 2 times by half times by m times by x3 dot, or m x3 dot. The derivative of this term with respect to time is m x3 double dot. And the derivative of t with respect to x3 is 0 because t is not a function of x3. And the kinetic energy here is only a function of the velocities. So again, this term is 0 and this term will be disappear in the Lagrange equation. The partial derivative of v, or potential energy, with respect to x3, the first term is not a function of x3, the second term is not a function of x3, and only the third one and the last one will be considered in this derivative. The derivative of this term with respect to x3 is equal to 2 times by half times by k times by x3 minus x2. This term 2 will be cancelled out with half, and plus the last term, which is again 3 times by k times by x3. Now we can substitute these terms into the Lagrange equation and extract the last equation, which is the third equation of motion in your system. So here in this case, you can see we used the Lagrange equation to extract the equation of motion. Of course, this is a simple system, and you can also use the Newton's second law to extract the equation of motion. But you will see in some complicated examples, it's not that easy to extract the equation of motion by using the Newton's second law, and we prefer to use the energy methods and Lagrange equations. So in this system, we have 3 equations of motion. And now you can, if you want to solve these equations, you can write it in the matrix form. And today we will discuss the procedure of the solution for this type of systems. Okay, any question from this example? Is it clear? Okay, here the next example, we deal with somehow a complicated system. We want to derive the equations of motion of the trailer compound pendulum system shown below. Here we have a trailer which includes a compound pendulum. This system is moving with a velocity of x dot and acceleration of x double dot, and at the same time this compound pendulum is moving and is rotating, in fact, about point O with the angular velocity theta dot and angular acceleration theta double dot. This is a system with 2 degrees of freedom because we have this pendulum. It's not a simple single degree of freedom system, and we have 2 degrees of freedom. We can consider x, t, and theta as the generalized coordinate system. To extract the equation of motion for this system, the best option in this case is the energy method and Lagrange equations, because when you want to write the Newton's second law, it's not very easy to write the equation of motion and write the force and moment equation, because you deal with a rigid body, dynamics of a rigid body, and it's a little complicated. So we want to solve this problem by using the energy method. For this purpose, we need to write the kinetic energy and potential energy for this system. As you can see, we deal with a pendulum. I mean, when you want to write the potential energy, the weight of this pendulum will appear in the potential energy terms, because if we assume that this is a pendulum which is rotating about 1 point, and this is the mass center of the pendulum. If we assume this is the initial position for this mass center during the vibrating motion, this mass center will go up and down and its position will be changed. And it's not similar to a system with a spring. I mean, for example, when we have a spring system and mass, assume for example this system, we neglect the weight in the potential energy, because this weight will create some initial deflection in the spring. So in the potential energy, we do not consider this mass. But here in the pendulum, this mass and its variation in the height will appear in the potential energy. And also we have one spring here, K1, one spring K2 here. So both of them will appear in the potential energy. For the kinetic energy, we have one trailer with mass m, which it has only a translational motion with velocity x dot. So the kinetic energy will include 2 terms. One is due to the mass of the trailer, this uppercase mass m, and the other one is due to the rotation of this pendulum. This pendulum has a general motion, in fact, a combination of translational and rotational motion, because point O is moving with the velocity x dot. This point O is fixed on the trailer, but at the same time, this pendulum is rotating about this point. So this pendulum has a rotational motion as well as the translational motion. So the kinetic energy of this pendulum will have 2 components, one due to the rotational motion and the other one is due to the translational motion. And you know, from dynamics, you can write this kinetic energy about the mass center or about the fixed point O. And finally, we have 2 dampers, C1 and C2, and also we have the external force Ft and one external moment Mt, which create some change into the Lagrange equation, and it's not a conservative system, so we need to calculate the Q, the uppercase Q, for the degree of freedom x, t, and theta t. So let's solve this example to see what should we do. As I told you, the first step, we need to calculate the kinetic energy. this kinetic energy will include two terms. The first term is the kinetic energy for the trailer, and the second part is, which includes two terms, is the due to the rotation and translation of the pendulum. This VC is the velocity of the mass center for the pendulum, and theta dot, which is the angular velocity, the derivative of this theta with respect to time. This J is the mass moment of inertia for the pendulum about its mass center. And this M, lowercase m, is the mass of the pendulum. And the uppercase M, which is the mass of the trailer, as it is mentioned here. So this is the kinetic energy for this system. We need to calculate VC, which is the velocity of the mass center. In fact, the main challenge or the most important point in this kinetic energy is to calculate the VC. For this purpose, we can write the position of point C. Also, you can use the relative coordinate system from dynamics. I mean, for example, you can assume a relative coordinate system on this point O. For example, we can call it X and Y. And then you can write the relative velocity equation between point C and point O and write the relative relations for the velocity in this coordinate system, and finally extract the absolute velocity for this system. But here I will use maybe a little more simple method, and I want to find the velocity of the mass center by using this method. For this purpose, we obtain the position vector of this point C here. The x component of this position vector is x plus L over 2 times by sine theta. You know that this length is L over 2. Let me so this length, sorry, okay, this one is L over 2, half of the length of this pendulum, and this angle is theta. So if we want to measure the horizontal position of this point C, it's equal to xt, because xt is the horizontal position of point O. And if you assume that, for example, this is your coordinate system, x and y, your x position is equal to the xt, the xt lowercase xt plus L over 2 times by sine theta, which is this length. Okay, so this is the horizontal position of the mass center, and the vertical position is L over 2 times by cosine theta, which is this length. Let me show you with another color. This length is the vertical position for C. Of course, it depends that where is your origin of this coordinate system. I assumed that the origin of this coordinate system is located in the initial position for the trailer, and the y position is exactly located on this datum level. Okay, so y, of course, here we can have one minus, but because we want to calculate the velocity, this negative does not have any effect on our calculation. So the next step, we need to calculate the VC, as I told you, and this VC is the derivative of the position, or the velocity of the position C is equal to the derivative of the displacement of this point. The displacement is x and y, or vector r, and now to calculate VC, the velocity in horizontal component is the derivative of x with respect to time, and the velocity in vertical direction is the y component derivative with respect to time. So we can calculate VC, which in fact this is the horizontal component, x dot plus L over 2 theta dot cosine theta, and the y component or vertical component is minus L over 2 theta dot sine theta. Now we can substitute VC squared. You know, when you have a vector in this form, I mean, for example, VC is in the form of x I, which I is the unit vector in horizontal component, and y j, the VC squared or the amplitude squared of this vector is equal to x squared plus y squared. This is from the vector algebra, you know it. So VC squared, which is the amplitude of the velocity of the mass center for this pendulum squared, is equal to its horizontal component squared plus its vertical component squared, and horizontal component is this term and the vertical component is this term, so we can substitute here. And for the J, which is the mass moment of inertia about the mass center, it's equal to 1 over 12 ml squared. Now we can substitute this value and simplify the kinetic energy. As you can see, I substitute, and finally this term is the kinetic energy for the system. For the potential energy, we have two springs, half k1x squared, half k2x squared. And as I told you, we have the weight in the potential energy, and it's equal to mgl over 2 times by 1 minus cosine theta. This is the potential energy of the system. And now we need to calculate Q1 and Q2 because we have a system with 2 degrees of freedom. We will have Q1 and Q2. Q1 is Ft times minus C1 x dot minus C2 x dot. Q1, you know, that is in fact the force acting in x direction. We have a negative sign for the C1 and C2 because you know that the direction of the force of a damper is always opposite of the direction of motion. I mean, when your mass is going to the right, the direction of the force of the damper, which is C1 x dot, is always in the opposite direction of the motion. So we will have one negative in Q1 for C1 and C2, and for the Q2, which is the force acting in theta direction, we will have only the moment mt because theta is the angular rotation and angular degree of freedom. So the force acting in this direction should be considered the moments in fact, and we will have only mt in this system. Now we can substitute for Q1 and Q2 respectively x and theta as the generalized coordinate system and substitute into the Lagrange equation. We need to calculate the partial derivative of t with respect to x dot, the partial derivative of t with respect to x, the partial of v with respect to x, and finally Q1. And we can substitute and extract the first equation. The partial of t with respect to x dot will calculate it from here. This term does not have x dot, so the derivative is 0. Here in this term we don't have x dot, and only in this term, the second one and the first one, we have x dot. You can calculate the derivative of this term with respect to x dot, which is m plus mx dot plus half times by ml theta dot cosine theta. This term is the partial of t with respect to x dot. And now we need to calculate the derivative of this term with respect to time. M plus m is a constant value. The derivative of x dot with respect to time is x double dot, this term. And here we have half ml times by theta dot cosine theta. Theta dot is a function of time, theta is a function of time, so we will have the derivative of the first function multiplied by the second function plus the derivative of the second function multiplied by the first function. So we will have half times by m times by l, the derivative of theta dot, which is theta double dot, multiplied by the second function, which is cosine theta, and plus half times by m times by l times by theta dot, multiplied by the derivative of cosine theta with respect to time. You know, the derivative of cosine theta with respect to time is minus theta dot times by sine theta. We have another theta dot, so it will be theta dot squared, and this is the derivative of this term. So this is the derivative of partial t with respect to x dot with respect to time. The partial of t with respect to x is 0 because there is no x in the kinetic energy. The partial of v with respect to x can be calculated from this term. We have half k1x squared, half k2x squared, and you can substitute, so it will be k1 plus k2 times by x. And for q1, which is in fact the force acting in x direction, we will have ft minus c1 plus c2 times by x dot. This is the q1, and we can substitute into the Lagrange equation and extract the first equation. As you can see, this is the first equation. For the second equation, we need to substitute, instead of q, we need to substitute theta and calculate the derivatives. You can calculate all of the derivatives similar to the x, but only the derivative of t, this term here, is not 0. While in the previous equation, the derivative of t with respect to x was 0. But here we have theta. As you can see, we have cosine theta, we have sine theta. So the derivative with respect to theta for the kinetic energy is not 0. We need to calculate this. And here in this term, we have theta, and also in this term. So we need to calculate the derivative for with respect to theta. And it's equal to this term, the derivative of t with respect to theta. And if you simplify this, you can extract this term. And finally, you can calculate all of the partials and substitute into the Lagrange equation and extract the second equation for this system. As you can see, this is the Lagrange equation. This is still a little complicated, especially when you want to calculate the kinetic energy. But if you wanted to use the Newton's second law, it's more complicated, and you need more calculations to extract the equations of motions. Okay, so this is the general procedure to use the Lagrange equation to extract the equation of motion for the systems with a multi-degree of freedom. And most of the time from now, we try to use this method even for the system with single degree of freedoms. Okay, if you have any question, please ask. Otherwise, we can wrap up this session and we can continue next week, because tomorrow is again a public holiday and we continue on Monday. Any question from these topics? Okay, no questions? Okay, thank you for your attention and have a good weekend and a blessed Diwali. And thank you. See you on Monday again.